Okay. Next, we consider the case that capital F r equal to 0 has real roots. So suppose it has two real roots. Suppose the possibly larger one is r plus. Of course, r minus and r plus can be equal. Okay. Anyway, the possibly larger one we denote by r plus. Okay. Then, since n is equal or greater than 1, so r plus plus n will never equal r minus. Therefore, capital F r plus plus n will never be 0. So in the recurrence relation, we take r equal to r plus. We can determine a1 from a0, and then determine a2 from a0 and a1, and so on, and determine an from a0, a1, a2 until an minus 1. So we can determine all the coefficients an. Okay, so this gives us a solution corresponding to r equal to r plus. That is this solution. Okay, the coefficient for r equal to r plus determined from this recurrence relation we denoted by an r plus. Okay, so this is a solution. But we are considering a second order equation. We want to find another solution. So how to find the other solution? There are some problems to be solved. So firstly, the simplest case is that r minus is less than r plus. These two roots, the two roots of capital F r equal to 0 are not equal. Suppose r minus, because we had already assumed that r plus is the possibly larger one. Therefore, if they are not equal, we have r minus less than r plus. And also we require that r plus minus r minus is not a natural number. That is, r plus minus r minus is not a positive integers. Then, as before, for r minus, for r equal to r minus, capital F r minus plus n will never 0. Okay, because the only 0 of capital F is r plus and r minus. But because r plus is not an integer, a positive integer, plus r minus, so r minus plus a positive integer will never equal r plus. Therefore, this will not be 0. Okay. So since this is not 0, as before, we can determine all the an using a0, a1, a2 until an minus 1 from this recurrence relation. Okay, because the coefficient of, for r equal to r minus, the coefficient of an is not 0. Okay, so this enables us to determine all the an using a0 equal to 1. So we obtained another solution corresponding to the index r equal to r minus, and the coefficient of the resulting coefficient an we denoted by an r minus. So this is the simpler case. If the two real roots are not equal and their difference is not a positive integers. Okay, so this is the first case. The case that r minus equal r plus, or their difference is a positive integer. In these two cases, this will not be true. Okay. For example, if r plus minus r minus is positive integers, then this is 0. So f r minus plus n might be 0 for some n. Okay. If that is 0, the coefficient of an is unknown. Is 0. Okay. If capital F r minus plus n is 0 for some n, then the corresponding coefficient of an is 0. So you cannot using this recurrence relation to determine the an. So this will raise some difficulty. Okay. So this we will discuss later. So now we concentrate on the case that r minus less than r plus. So before we proceed, we make some comments. The exponent r plus and r minus determine the qualitative behavior of the solution. as we can observe, the solution y plus is an we are looking for a solution of the form xr multiplied a power series. The r, as we, from our previous discussion, the r can only be r plus and r minus. Okay, so this might be singular, but the function to multiply to produce the solution is a power series which is analytic at zero. Such a function has very good properties near zero. So the interesting and non-trivial property are determined by the singular part of the solution. That is the xr plus and xr minus. Okay, xr minus. Therefore, the r minus and r plus is very important to determine the qualitative property or behavior of our solution. And the r plus and r minus are roots of the initial equation. That is, they can be determined by solving this quadratic equation. Here, the coefficient P0 and Q0, in the case P0, Q0 is the P0 and Q0 are the coefficient of the zero order term of the power series expansion xpx and x square qx small px and small qx. Okay, in the case that capital F, in the case that capital P, capital Q, capital R are polynomial, and x equal to 0 is a regular singular point. As we mentioned before, this P0 is the coefficient of, is the limit of this function, and this Q0 is the limit of another function. So when PQR are polynomial, we don't need to make a power series expansion of any function. We simply determine the coefficient small p0 and small q0 using these two limits and obtaining a quadratic equation. Solving this equation, we obtain the r minus and r plus. They determine the qualitative behavior of our solutions. Okay, so let's have a look on this example. So for this equation, this is a variable coefficient linear second order homogeneous equation. The capital P is the coefficient of y double prime, which is 2x 1 plus x. So qx is 3 plus x and rx is minus x. Okay, then we see that singular point is the point where the coefficient of y double prime is 0. So we see that singular points are x equal to 0 and minus 1. So we consider the case the first singular point, that is x equal to 0. Then we compute the coefficient small p0, which is this limit. This limit substituting our qx and px into this function. That is, we are requiring to evaluate this limit, and this limit is easy to find. That is 3 over 2. Similarly, q0 is the limit of this function, which can also be easily evaluated, which is 0. Therefore, our initial equation is the polynomial is capital Fr, which is r minus 1 plus 3 over 2r. So let capital Fr equal to 0. We can solve for the root. That is our r minus and r plus. R minus is negative minus 1 over 2. R plus is 0. Okay. So by our previous discussion, because r plus is not equal to r minus and their difference is not positive integers, so we can determine solution y plus. That is the power of x is r plus. R plus is 0, therefore that is x to the power 0 multiplied a power series. I'm sorry, maybe there should be n from 1, not from 0. Because if n is 0, then this can be combined with the constant 1. Okay, so this is n from 1 to infinity. So the first equation y plus is x to the power r plus, that is 0 multiplied this power series. So we see that y plus is an analytic function because x0 is simply 1. So y plus is equal to the power series, therefore analytic at 0. And y minus, for y minus, the singular part appears present, that is minus 1/2. Okay, so y minus is this function which is singular at origin, x equal to 0, multiplied by a good function that is an analytic function. So as before, this should be from 1 to infinity. Okay, so another singularity is x equal to minus 1. So for x minus 1, we perform the same argument. Firstly, we determine the coefficient P0. So you should evaluate this limit. X goes to the singularity, and then x minus 1, that is x plus 1, multiplied this, and this can be easily computed. That is minus 1. And for Q0, that is this limit. So substituting our capital R and capital P inside, we will lead to this limit, and this limit can also be easily computed. That is 0. Okay, having computing P0 and Q0, we write the polynomial, quadratic polynomial for the initial equation, that is capital FR. So capital FR is this, and let capital FR equal to 0. We are easy to find R0, R minus is 0, R plus is 2. That is easy. Therefore, for R plus, we have the solution of this form. X minus the singularity to the power 2, that is R plus, multiply a power series. Okay. And okay, this should also be from 1 up. Okay. And for R minus equal to 0, because the difference between R plus and R minus is 2, which is a positive integers. So we don't know whether the equation has a solution of this form. For this, we don't know. Okay, we don't know whether the equation has a solution of this form. So our remark is that if we only want to find some qualitative behavior of the solution near singularity, we don't need to solve the equation explicitly. That is to say, although we can write the form of the equation, so for this equation, for the two singularity of this equation, for the singularity x equal to 0, we can obtain the precise form of the equation, but we don't need to determine that the coefficient in the power series appears in these solutions. Okay, without writing the concrete value of the coefficient, we can study some behavior of these two solutions. Because, for example, y plus is a very good function near the singularity x equal to 0. Okay, because it is an analytic function near 0. But another solution, y minus, is not good because it develops some singularity at x equal to 0. So this part of the y minus is unbounded, goes to infinity when x goes to 0. So even we have not solved the equation, we can analyze the behavior of the solution. This is the advantage of this method. And for another singularity, x equal to minus 1. So for this singularity, we have a good solution. Okay, that is y plus. This is a second order polynomial multiplied an analytic function. Okay, so this is a very good solution, but we don't. For the other solution, up to now we do not have enough information. So we need to, because this is the exceptional case we have considered, we need to further study to see whether to observe the second solution of our equation near the singularity x equal to minus